Hello again, ladies and gentlemen. We are now at 6-2 substitution. This is page 344 on your textbook. Now, our last section, 6-1, was a whole lot of definitions. It was almost completely definitions and then figuring out what to do with those definitions. This section is almost completely work, and I'll be honest with you, I love substitution. This is one of the most fun things in algebra to me because I'm a big geek, and I love moving numbers around and seeing what happens. I love doing this. This is fun to me. Yeah, I know, that makes me really weird, but that's okay. So this is how you do substitution. Honestly, I think the best way to learn this is by doing the examples, but I'll give you a step-by-step first. Take the notes for the step-by-step, but to me, it's just doing lots of examples. It's going to get you there. Step 1, if necessary, solve one equation for one variable. For instance, this is what they call solve for y in terms of x. Now it says if necessary because it might not always be necessary. If you have slope-intercept form is always y equals mx plus b. So if it's already y equals something, hey, you're golden. You're already there. Step 1 is done for you. Step 2, substitute the expression from step 1, which may already be done for you, to make an equation in one variable. This will make a lot more sense when you see an example of it. But you could just copy it down for right now as far as what your instruction is. Oh, and I just had to add this. You got to make sure you solve for that variable when you do step 2. That's very important because we need a number value. Then step 3, we substitute the numerical value we get in step 2 into either equation. We can use either equation at this point. We're just solving for the other variable in our two-variable equation. Then we solve for the remaining variable. And so now we would have numerical values for both steps, or for both variables, and then we write the solution as an ordered pair. So if you're writing the solution as an ordered pair, what type of system is this going to be? This is going to be a consistent, independent system, a system that only has one solution. So we arrive at our first example. Use substitution to solve the system of equations. We have y equals 2x plus 1 and 3x plus y equals negative 9. Well here, as I said in the previous one, you may have, if you have slope-intercept form, you already have the y solved for. So we are going to use substitution to rewrite the second equation. The second equation, instead of 3x plus y, we're going to write 3x. So I'm working with the second equation right now. 3x plus, well, instead of y, I know y is equal to 2x plus 1. So I'm going to write 2x plus 1. And then I'm going to finish out the second equation, which is equals negative 9. So now I have substituted the value for y for my first equation into my second equation, and that makes it so that this equation now is only one variable, and I can solve for one variable. So now I'm going to simplify this. 3x plus 2x is 5x, and I've still got my plus 1 equals negative 9. Now I need to subtract 1 from both sides, so I'm going to have 5x equals negative 10. And now to get x by itself, I need to divide by 5. So when I divide by 5, I get x on this side. When I divide by 5 on the left side, I get x equals negative 2. So now I'm going to take this value, x equals negative 2, that I found from substituting, and I'm going to push this back into my first equation. So I've got y equals 2 times, well, I know x is negative 2, so instead of putting 2x, I can put 2 times negative 2. And then I've still got the plus 1. So now I'm going to simplify this. Y equals 2 times negative 2 is negative 4 plus 1. So y equals negative 4 plus 1 is negative 3. So y equals negative 3, x equals negative 2. So this point is negative 2, negative 3. And that solves the system. So here's another system. We have, this is 1a on page 344 still. I've got y equals 4x minus 6 and 5x plus 3y equals negative 1. I can already substitute. I don't have to do step 1 because step 1 is to find what y equals, and I know y equals 4x minus 6. So I'm going to substitute that directly into the second equation. So I'm going to rewrite the second equation. 5x plus 3y equals negative 1. And so now I'm going to substitute for y. 5x plus 3 times 4x minus 6. Because I know y equals 4x minus 6. It says it right there in black and white. But I still have to write the rest of the equation. Equals negative 1. Now I need to distribute here. So I've got my 5x plus 3 times 4x is 12x. 3 times negative 6 is negative 18. Equals negative 1. Now my 5x plus 12x is 17x. Minus 18 equals negative 1. I add 18 to both sides to get 17x on the left side. On the right side, negative 1 plus 18 is 17. So that gets me x equals 1. So now I know x equals 1. So I'm going to substitute that back. You know, and this time I'm going to substitute it into the second equation. It makes no difference which equation I substitute it into. I just want to find the value for y since I have the value for x. So I'm going to rewrite my equation. 5x plus 3y equals negative 1. And then I substitute my value for x. 5 times 1 plus 3y equals negative 1. 5 times 1 is 5 plus 3y equals negative 1. I need to subtract this 5, so I subtract 5 from both sides to get 3y on this side equals negative 1 minus 5 is negative 6. Then I divide by 3 to get y by itself. Y equals negative 6 divided by 3 is negative 2. So I know this, x is 1, y is negative 2, so I write it as an ordered pair, and my answer is 1, comma, negative 2. So now we have example 2 on page 345. Now this one is a little bit trickier because it does not start out with 1 in slope-intercept form, so it doesn't tell me what y equals right off the bat. So I need to choose to solve for either x or to solve for y. In this first equation, see, there's ways that you can make things easier on yourself. There's no particular way that you have to do this. That's one of the nice things about algebra, is as long as you follow the rules, there's many different ways you can solve a problem. But there are some ways that make things easier and some ways that makes things harder. For instance, in this here, I see I only have a single x right here. So I'm going to solve for x in terms of y, because then I'm going to make it easier on myself. So I'm going to rewrite the problem. X plus 2y equals 6. I want to get x by itself. Does it matter if you get x by itself or y by itself? Absolutely not. Makes no difference whatsoever. So I'm going to subtract 2y from both sides to get x equals 6 minus 2y. So I'm done with step 1 because I have solved for one of the variables in terms of the other. So now my step 2, I'm going to use my new value for x to plug into this second equation. So first I'll rewrite the second equation. 3x minus 4y equals 28. Now I've got a big hairy thing to write for x. I'm going to write 3, and instead of x, I'm going to write 6 minus 2y. Because x and 6 minus 2y are the exact same thing. So I can just substitute it. Then I finish writing my equation. Minus 4y equals 28. Now I have to distribute my 3. 3 times 6 is 18, minus 3 times 2y is 6y, and then I do my minus 4y equals 28. Now I simplify with my y's, so I've got 18 minus 10y equals 28. And then that changes to, let's see, I need to get rid of the 18, so I subtract 18 from both sides to get negative 10y equals, subtract 18, I get 10. And now I divide by negative 10 to get y by itself equals negative 1. Boy, that was kind of a long way to get there, but you know what? Now that I've found out that y is negative 1, I can plug it back in right here, and I can find my value for x. So I'm going to rewrite what I wrote earlier. Or you know what? I can go either here, I can go into this part, I can go up into this part. There's many places I can substitute that have both x and y to find out what my x value is. As long as I was careful and didn't make mistakes, it really doesn't matter where I go. So you know what? I'm going to go back into the whole first equation. So I'll rewrite that first. X plus 2y equals 6. So then I'm going to plug in my new value that I know for y. X plus 2 times negative 1 equals 6. X and then plus 2 times minus 1 is going to be minus 2 equals 6. And then I add 2 to both sides to get x equals 8. So I know x equals 8, y equals negative 1. So my answer is 8, negative 1. Okay, now I'm going to show you a couple strange cases, and I'm not going to tell you what they are in advance, but you'll be able to see it pretty quickly here. Here in this example number 3 on page 345, we're back to having, they're being nice to us again. They're giving us y equals 2x minus 4. So they did the first step for us already, so I'm just going to substitute that. I'll rewrite my second equation, so it's negative 6x plus 3y equals negative 12. And then I'm going to substitute for y, so I'm going to do negative 6x plus 3 times 2x minus 4 equals negative 12. And then I'm going to distribute my 3, so I got negative 6x here, plus 3 times 2x is 6x, 3 times negative 4 is negative 12, equals negative 12. Now here's something weird. I've got minus 6x plus 6x. I've got no x left. And all I'm left with is negative 12 equals negative 12. Now that's true, but how does that help me? I just have a true statement. Well, what we found, this is the weird thing that's going to happen when you have a system that is dependent. So how many solutions does a dependent system have? It has an infinite number of solutions. So this, when we get a true statement that doesn't have anything to do with x and y, it's just true. Negative 12 equals negative 12. Well, yeah, of course it does. Then we know we have infinitely many solutions. Whatever values we put in there for x and y will work. So this is your other weird case. If you're following along from the last section, you probably know what's going to happen here already. But we've got 2x minus y equals 8 and y equals 2x minus 3. So they're nice to us. Whoa. They're nice to us here again because we know that y equals 2x minus 3. So I'm going to start just by substituting that. I'm going to rewrite my first equation, 2x minus y equals 8. And then I'm going to substitute for y. 2x minus 3 equals 8. Then I'm going to distribute my negative sign. 2x minus 2x plus 3, because we're subtracting a negative 3, so it's plus 3 equals 8. Now something really weird happens, because I've got 2x minus 2x. Well, I've got no x left. So that's what happened to us last time, but look here. I'm left with 3 equals 8. No it doesn't. 3 has never equaled 8 in any math that I know of. So this is an incorrect statement. So since it's incorrect, I know that there is absolutely no value of x and y that I can put in that will make it true. So this is an inconsistent system which has no solutions. Because there is absolutely nothing I could do for x and y that would make this statement true. 3 never, ever, ever equals 8.